So in the last week, we discussed about characteristics of laser beam, which are generated by the laser source. And further, we talk about single pulse limitation and multi-pulse facility within the receiver to identify many pulses which can be fired in a series. Okay. And further, we derived a relationship between the parameters like pulse firing rate and flying height and how they are related. So in our discussion, we see that there is a trade-off scenario. Okay. And trade-off on the basis of quality of the data. If you want high quality data in terms of dense point cloud, then you need to fly at lower altitude. Okay. And if you want to collect the data at low cost, then you need to fly at high altitude. But in that case, what will happen? The quality of data in terms of point density will decrease. Okay. So so what is the conclusion we have? The first conclusion is high quality data. Okay. In terms of dense point cloud and high accuracy. To obtain this, fly the aircraft at low altitude. Okay. And the second one, for cost effective data acquisition. At cost effective in terms of low cost. Okay. Fly at the higher altitude. But at the expense of what? Lower data quality. Lower data quality, if you fly at higher altitude, then obviously what happens? The distance between the laser source and target increases. Okay. So in that case, the larger distance the laser beam needs to travel, so that further lead to the lower accuracy in the position calculation. So there will be large error in XY, that is planimetric position, and as well as the Z, that is at what height, what is the vertical position of that point. Okay. So accuracy will decrease. Accuracy decreases. And at the same time, the lower data quality means data density also decreases. Okay. So based on the few derivations in the previous lectures, I'm giving you a problem and kindly solve it and let me know the solution for that. In case of airborne laser scanning, aircraft is flying at altitude, we call it AGL, above ground level. Use this height h is equal to 1000 meter, and the laser scanner that is inbuilt with the laser scanning system has single pulse limitation. Okay, then calculate the pulse firing rate max that we can obtain. Please solve it and raise your hand.
Sir, please load the slide, please.
Okay. Okay, once you are ready with the solution, please let me know. Okay. Because I have shared my slides, so I'm not using this MS Teams application directly. So I can't see if you raise your hand. So please speak like you have solved it.
So 1,50,000 per second.
Okay. So we can say it's 105 kilohertz. It is
Yes, sir.
150. 150 kilohertz. Is it?
Yes, sir.
I would like to get response from other students as well.
So 1,50,000.
Okay. Yeah, Alok. You told that 1,50,000.
Yes, sir.
Sir,
Good,
Arun sir
good.
also.
Okay, good. Sunil.
150 kilohertz.
150 kilohertz. Good. Praveen, what's about you? Have you solved it? Praveen, could you please unmute?
Yes, sir.
बताइए, solve कर लिया आपने?
No, sir. Little bit time more.
ठीक है, take your time. Let me know what answer you are getting. Shivam.
एक मिनट सर.
Ruchi, could you please unmute?
Yes, sir. Sir, I was absent in last class. That's why I can't solve it.
Vibham,
Yes, sir. I have solved it.
uh, how much you got? This pulse firing rate?
So I got 150 kilometer.
Not kilometer, it's kilohertz.
Yes, sir.
Yes, Vardhan?
Oh, sorry, sir. I was absent in last class. That's why I am not able to solve the problem.
Fine, if you were absent, all of you, those who were absent in the last lectures. So did you contact your batchmates like what was taught?
Sir, done.
How you solve, Praveen?
Sir, C upon 2h. So 3 into 10 power 8 upon 2 into 100. So then, sir, solve it 150 kilohertz.
Yeah, correct. So this pulse firing rate maximum that we obtain is equal to C divided by 2S, is it? And all of you, please listen, those who were absent in the previous lecture. The detailed discussion you can talk with your batchmates. But see over here, this pulse firing rate maximum is related with this flying altitude h. Okay, so if you increase this flying altitude, what will happen? This pulse firing rate will decrease. So this h value is given, and the medium is air. So this speed of laser beam is considered as speed of light c. So 3 into 10 to the power 8 into, and your speed is 1. It's 10 to the power 3. So what you will get? 1.5 into 10 to the power 5. It's 150 kilohertz. Okay. For the same problem, if this laser scanner electronics is improved such that this LS system can fire 3 beams, 3 laser pulses in series before receiving the return of the first pulse. So it's n is equal to 3. In that case, what will be this pulse firing rate maximum?
So 450.
So, four lakh 50,000.
Correct. It's a 3 times. So if you see the derivation, which we have derived, it's NC. Okay. So it's kind of multiplication by factor 2, by factor 3. So multiplication by integer number. Okay. N. In case of single pulse limitation, N is equal to, in this case, N is equal to 1. Okay. But if your sensor has capability to identify multiple pulses at a time, okay, and let's say internal electronics has capability, this receiver unit has capability to identify 3 pulses. Okay, so if n is equal to 3, identification of 3 pulses means in a series the three laser pulses are fired. Okay, without waiting for the return of the first pulse. So 3 pulses are in air. Okay, after that, the return of first is received at the receiver. It is called as this multi-pulse identification facility within the receiver. So in that case, your formula will be NC by 2H. So if n is equal to 3, this become, you multiply it by n, and here n is equal to 3, so it's 4.5, so 450 kilohertz. Okay. Now, in the entire analysis, we talk about data quality, and one parameter we consider, that is point density. Okay. Now we are going to see how these parameters are related with the point density. We'll derive the formula. Okay. And that formula gives us idea that, let's say, if you change the field of view, if you change the pulse firing rate, if you change this scan rate, flying altitude, then how point density is affected. Okay. So we'll derive that equation for point density. So the unit of analysis over here is point coordinate. So this is the reason why we call it point density. And when we calculate the density, then it can be in 1D, 2D, and 3D. Okay. So 1D, we call it line density. Okay. 2 dimension, it's called area density. Okay. While in 3D, we call volume density. Okay. In our analysis, we consider the first two, that is line density as well as area density. So if we start with the line density, then combining the line densities we obtain, we'll see the average area density, what it will be. Okay. So we have already discussed the architecture, into the geometrical architecture of this airborne LiDAR system, as well as how it fires the laser beam, what is the area that is covered along one flight line. Again, I draw that schematic over here. So let's say this is the ground terrain. Okay. And over the ground terrain, this aircraft is flying at the speed of V. Okay. And this is the nadir point, let's say. And this flying height is H. Now, the field of view. The field of view of laser sensor is, let's say I write it FOV. So this is the field of view FOV. It can be represented by symbol theta over here. Okay. So this is the area strip that is covered along a flight line. Okay. So the direction in which this aircraft is flying, it is called as, when you project it on the ground, let's say if you project this trajectory of flying aircraft on ground just below it, this nadir point I have considered over, this will be here. It is called as flight line. Projected on ground. Ground projected, you can write. Okay. So it's flight line. This is the width This is the width of this area strip that is covered along one flight line. Let's say we call it W. Okay. And this W is also called as swath. So the terminology swath is used to indicate the width of area strip that is covered along a flight line. Okay, covered along a flight line means that area, the laser beams are hitting in that area. Okay, at a uniform spacing. If you see that, then these are the laser footprints. Okay, and these laser footprints are the target points where the laser beams are, laser pulses are hitting the ground. Similarly, next line you have when this the platform progresses in forward direction. Who will tell me why I have drawn the slant line? Why these laser footprints are along a slant line, not along this like perpendicular line across the boundary of area strip?
Sir, more area will be covered.
Listen carefully. The width, this swath, I have defined this line perpendicular to the boundary of area strip. Fine. While this is a slant line, these laser footprints are hitting the ground along a particular line. It is called as a scan line. Okay, but this, why this scan line is slant? It's not along this. Why it is not like that? Why it is not perpendicular to the boundary of this area strip? We have already done discussion on this. Vibham, could you tell me?
Sir, the reason which I am thinking is that because of the field of view. So when the laser light hit, it will be hit along the line which is parallel to the field of view. So this is what I'm just thinking, sir.
Okay, fine. See what happens. Let's say at time t is equal to t1. Okay, this LiDAR system is initialized and first laser pulse is fired. And this first laser pulse hit over here. So this is the first laser pulse at time t is equal to t1. Okay. Now what happens? The next laser beam is fired at time t2. Okay. What will be this t2 minus t1? After what time the next laser pulse is fired? T2 minus t1. It is a time period. If I draw over here, then the first laser beam, let's say if you are considering over here. So what happened? The second laser beam is fired after time t2. So this distance is how much? This is the time period. Am I correct?
Yes, sir.
Okay. So this t2 minus t1, let's say if you are considering this rising edge, okay, then this difference is also t, it will be equal. So either you can may take reference the rising edge, or you can take reference the maximum at which this maxima of that laser pulse, time at which the maxima is obtained. So this is also T. Okay, so T2 minus T1 is T. So after capital time T, that is time period of that laser beam, the next laser pulse is fired. Okay, but what happened? This in between T2 minus T1, this aircraft is moving at a speed of V. It moves to the next location. Okay, now when second laser beam is fired, it will be in the forward direction over here. It will be over here. If I ask you, let's say if I zoomed in this over here. So this is the laser footprint at time T2, and this is at time T1. This is at time T1. T2 is fired after time period T. By that time, the aircraft moves in a forward direction. What will be the shift in a forward direction between these two? Who will tell me? What will be the shift in the forward direction?
So V into T2 minus T1.
Correct. So it will be, the shift will be, we can either write dT1 T2 is equal to speed of flying aircraft into T2 minus T1. Okay. Similarly, this next laser pulse after 2T time, then further. So there is an incremental shift in the forward direction. We can say this is D delta is equal to D T1 minus T2. See, this D delta is an incremental shift in forward direction. Forward direction, I'm assuming the in the direction of moving aircraft. So incremental shift in forward direction. Okay, so this is the reason why this scan line is not this vertical line, it's a slant line. Okay. But for our calculation, the line density, as I told that our objective is to calculate the point density, and we start with calculating the line density. Why we start with the line density? See, reason is that there is a symmetry of point distribution along the line in two directions. If you analyze how the laser footprints are hitting the ground, one symmetry you can see the scan line. Okay, here you can notice that the way laser beams are hitting the ground, they are across the flight line along a direction, along a particular line. Okay, so one density we can calculate along the scan line, and it's a 1D density, line density. What could be the next? Like at one direction we have decided along the scan line we calculate a point density. Okay, it is called as 1D, it's line density. Another reference direction can be taken as the forward direction in which this aircraft is flying. This one. And that we consider the flight line. Okay. So scan line in nomenclature, what we call along the scan line and across the scan line. See, though I'm using a word across and along, but it's not a 90-degree perpendicular to the these two lines are not orthogonal. Orthogonal means they are not separated by 90-degree shift. Okay, this is slant line. But in our calculation, what we do, we assume that this scan line is perpendicular to the flight line. That assumption we make for our further derivation or further calculation. So what we assume, this swath W, all these laser footprints are hitting along this swath W. Okay. So for ease in calculation, we do this. We use these assumptions. Okay. I hope it is clear to you. If there is any doubt, please let me know.
Hello, sir.
Yeah.
Sir, one more time repeat the time interval concept.
हाँ प्रवीण बताइए क्या पूछ रहे हैं आप?
Sir, one more time repeat the time interval concept.
नहीं किस टाइम इंटरवल का पूछ रहे हो?
सर वही जो फ्लैट लाइन पे मतलब जो हम स्कैन लाइन लिए हैं सर, वो जो पॉइंट है T1 T2 कर रहे हैं.
ओके. Let's say this box is representing the sensor location aircraft on board. Okay. So let's say this is the terrain. And these are the boundaries of area strip that is covered along a flight line. And this is the ground projected trajectory of flying aircraft. We call it flight line. Fine. At t is equal to T1, T is equal to T1, the system is initialized. So you switch on your LiDAR system at time t is equal to T1, and the first laser beam is fired. Let's say this laser beam is hitting over here. Okay. And corresponding to T1, what will be this range R1, and scan angle θ1 is recorded. Now at the second laser beam, if I plot this this point I am marking as T1. Okay. The second laser beam is fired after time t, that is capital T time period. This is time T2. Okay. So how much time is elapsed between T2 and T1? That is T2 minus T1. I'm considering over here capital T. Okay. This aircraft, this sensor system is mounted with the aircraft, and aircraft is moving in a forward direction at speed v. What will happen? The forward distance that is covered by the aircraft. Okay. Let's say this forward distance that is covered by the aircraft, what it will be? In capital time T at speed of v, how much distance is covered by the aircraft? Praveen.
सर T2 टाइम कवर
डिस्टेंस कितना कवर होगा? इन टाइम
जो
t
डिस्टेंस कवर होगा सर मतलब विद इन
let's say a particular object is moving at a speed of v. Okay,
यस
so in a capital time t, how much distance that object will cover?
कैपिटल
Let's say you are running at a speed of v. Fine. So in a time t,
yes,
how
sir.
much distance you can run? At a constant speed v you are running. In time t, it's a variable you can use. Let's say you are moving at a speed of 5 meter per second. It's not feasible. Like take in terms of variable, like you are moving at a speed of v. So in time t, how much distance can be covered? It is equal to v into t. Fine.
So
Distance d is equal to v into t.
d into t.
v into t, speed into time is equal to distance. पढ़ा है ना ये चीज?
Yes, sir.
ठीक है, तो ये
Yes,
in
sir.
capital time t, that is the time difference between pulse t1 and t2, the distance covered is at a speed of v is equal to v into t. Now at time t2, the location of this sensor has a new location, and it is in a forward direction at the next position, separated by the previous position by distance t. Okay. Now when the next beam is fired, what happens? It hits somewhere here. Okay. And this distance will also be same. Okay. When you project it, so it's a ground projected. These two laser beams are there. Okay. It also depends. This distance exactly, we can't say this is v into t. Okay. Because this is at a different angle theta, and this is the theta 2, and this is at theta 1. So there is angular deviation as well, but this distance is proportional to v into t. Okay, so this is the effect. Now it has a new position. Okay, once is fired the laser beam, then the next footprint will not be in the same line. Like this is the perpendicular line. So it will not hit over here. Okay, it will hit at a location in a forward direction next to this the first laser footprint. I hope it is clear now.
Yes, sir. It is.
Chalo, good. Okay. So what? So the two nomenclatures we have derived over here for the line densities. So two reference directions we are considering. The first one is along the scan line, and another one is across the scan line. Okay, across the scan line is considered as line along the flight. It's a flight line. Now we'll see when this is the area strip that is covered in one flight line, that is covered along the flight line. Okay, I have taken the assumption this is the swath. Okay, and We have our sensor over here. And this is field of view. If you see from the side, it's a perspective view. If you see, if observer is looking from this side, okay, so its view will be, this is your sensor system. This is the area strip, okay, and this is the scan line. Scan line. This is the nadir position directly perpendicular to the sensor. It provides you this height edge flying aircraft. This is FOV. I'm using symbol theta for this. Okay. And two other parameters are defined with respect to the sensor system itself. So that is if pulse firing rate. In 1 second, how many laser pulses are fired by this sensor system? Second frequency is scan frequency. Scan frequency means how many rotations are there by the mirror in 1 second. Because see what happens, if you see our discussion, if you recall our previous discussion, this is the laser source, continuously fire the laser beam. Now we have the mirror over here. Okay, and these mirrors rotate. What happens when this mirror rotates? This is the normal direction. Let's say this normal direction changes. And when this beam is hitting this mirror, there is a reflection. So angle of incidence is equal to angle of reflection. When this normal changes, always that angle changes. Okay. So in one rotation, like let's say this is confined. The rotation is confined within this. So how many rotations are there by the mirror in 1 second? It is called as scan frequency. Okay. So the mirror in 1 second, how many rotations are completed by the mirror is called as scan frequency. So it is represented by F scan. So F scan is the property of optics, rotating optics, while F PFR is a property of this. So this is the laser source. Just see. This is the laser source, and this is the optics. Okay. So the laser source, this F PFR is related to laser source, while the scan frequency is related to optics. Okay. And these are the integrated part of laser scanner. The rotating part, this optical rotating part, laser source, a laser transmitter. So all these are the individual components, integrated components of laser scanner. So these two frequency also we consider over here. Okay. This is the swath. The scan line, the total length of scan line is considered as swath. We have already discussed previously. So let's say if it is LS is the length of swath, length of scan line, it is swath. How much it will be? Point A and B, the distance between point A and B. How much it will be? Alok,
Sir, H sin theta.
hmm?
H sin theta. Mhm.
All of you solve it geometrically. Wow, how much it will be. This is the perpendicular line. And this is the midpoint of A and B. So this length, let's see if I represent this point as O. So AO is equal to OB. This is total angle is theta. All of you do the calculation and let me know what is length DAB. Please wait.
Sir, your screen is not visible.
Wait. I'm going to share again that screen. By the meantime, try to solve that.
Sir, 2 tan theta by 2.
Good. So it is this length. If you see O and B, so this length DO and B is equal to tan theta. This angle is theta by 2. Okay. So tan theta by 2 is equal to this length OB divided by H. So DOB is equal to H tan theta by 2. And I told that this length AO is equal to O and B. So DAB is equal to 2 times DOB. Is 2 times DOB. It will be equal to 2H tan theta by 2. So this is the length of a swath. So this length is known. Okay. To calculate a line density, what will be the requirement? Line density means how many points per line. Okay. So how many points per line? If I say this density, it's along a scan line. Density along. So density along is equal to total number of point capital N divided by swath W. Okay. It is equal to N. And what is length of scan line? We have calculated 2H tan theta by 2. Okay. How we calculate N? How many points are there? along these scan lines. Which parameters govern this?
Pulse firing rate, sir.
Correct. Pulse firing rate govern as well as this scan rate also govern this. Just see. Capital N is equal to number of points fired in 1 second PFR divided by number of scan lines in 1 second. What this formula gives you? If PFR, number of points per second, divided by number of scan lines per second, it is equal to number of points per scan line. If I write it, let me add a next page so that capital N is equal to number of points fired in 1 second divided by number of scan lines generated in 1 second. This 1 second will cancel out. The number of points fired divided by number of scan lines generated. Okay, 1 second is common. So this will be equal to number of points per scan line. And this is actually N. In one scan line, how many points are there? So this is equal to N. This is the equation. Let's say this equation first. And this is equal to this is equation second. Okay. So if substitute this second equation to the first, what you will get? Density along the scan line is equal to F PFR, that is capital N divided by 2h tan theta. So F PFR, F scan into 2h tan theta by 2. Now see, this is a density. If you want a high quality data, then obviously it should be high. So if you want to increase this density, then it's directly proportional to PFR. You need to increase it. You need to decrease the rotating speed of mirror. Then only you can obtain the high density along the scan line. Further, you need to decrease the flying height. We have already discussed over here. Just see. Data density will decrease when you fly at higher altitude. Okay. And this statement is supported by this formula. Data density will decrease. Wait. So this data density will decrease when you increase the flying height. Okay. Further, this angle theta, if you increase the angle theta, then if you see the curve of tan theta, 0 to pi by 2, it's a monotonically increasing function. So if you increase the theta, then entire tan theta will increase, and this will decrease the density. Okay. What does this mean? It means you should have a restricted field of view. Your mirror speed should be low, and you need to generate laser pulses at a high firing rate. Then only you can obtain a dense points along the scan line. Okay. Now the second reference direction, that is across the scan line. If I draw over here that across the scan line schematic, okay, these two are the boundaries of an area strip. This density we have calculated. Though I have drawn it in a slant way, but I assumed that it is vertical. Okay. Now another density is along. It means what is the spacing between these two? Spacing between these. How we calculate a spacing between these two successive points, the forward direction. See, this aircraft is moving at a speed of v. Okay. And how many lines are covered in 1 second? Okay. So if you divide v by f scan, tell me what this parameter will, what it is stating. The speed of platform divided by scan frequency. It tells us how many distance traveled in a forward direction in 1 second. Distance traveled in 1 second divided by scan lines in 1 second. Okay. What is this distance? This is a distance between two successive scan lines. You see, all these distances are constant. So this is a distance between two successive scan lines. So distance traveled in 1 second divided by scan lines in 1 second. It gives you like distance traveled in one scan line. Okay, when you go from the previous to next scan line, what is the distance traveled? That is given by v divided by f scan. Okay. And let's say this is a distance. It's not density, it's a distance across. Why I'm using across? Because the reference direction we have considered along the scan line. Okay, so it's a d across. So we can write it density across is equal to 1 divided by the distance across. Obviously, when you have a distance between two successive points, okay, if you take a ratio of this, you will get a density. So I'm giving you 5 minutes time, and please revise it. If there is any doubt, let me know. We'll discuss that. Okay, so let me know. Is there any doubt? Okay. So we have derived line densities along the scan line as well as across the scan line. And we have two equations. So the first equation for density along, it is equal to
Sir, screen
divided
share.
by it's the F scan into 2 into H tan theta divided by 2. So
Sir, screen is not visible.
okay. I hope now it is visible.
Yes, sir.
Okay, so density along the scale line, it's a we have derived it, and then density across. Okay, so density across is equal to what it is? Density across, it is equal to बताइए भाई आप लोग क्या कैलकुलेट किया हमने डेंसिटी अक्रॉस it is there.
Velocity of aircraft upon F scans.
No, that is d across. It's a distance between two scan line. It is there. It's a d across. When we calculate density across is equal to 1 divided by this distance. So it will be equal to F
1 by d
scan.
across.
Yes, F scan divided by V. Okay. What this mean? Like when we have a 2 points, 2 successive points, let's say these are the points. This is one scan line, second, third, fourth. Okay. And these are the points spacing between successive scan lines. Okay. If you calculate this distance d, then reciprocal of this density is 1 by d gives you the density, line density. Okay. It's 1 by d will be the line density. Okay. It is clear. Is there any doubt? Let me know.
Yes, sir, clear.
So
Sir, could
line
you share
density.
your screen?
Pardon?
Sir, your screen not visible here.
ये क्या किसी को नहीं दिख रही है क्या स्क्रीन?
Yes, sir.
हेलो.
शो हो रही है.
एक मिनट. I hope now you can see the screen.
Yes, sir.
Okay.
Yes, sir.
So this density across, when you calculate, it's 1 by d. Okay. And what D we have calculated? That is V divided by F scan. Fine. Let's say our interest is to have a uniform point spacing. Uniform point spacing meaning is that like these are the laser footprints we have along the scan line. Let's say, okay, and these we have across the scan line. Uniform point spacing means either along or across the distance should be same. Our point density should be same. So to get a uniform point spacing, if I write this uniform point spacing, what should be the condition? This you need to just equate 1 is equal to 2. Under this condition, this you can obtain the uniform point spacing. Okay, so you need to select all these parameters in such a way that they satisfy this criteria. Let's say this is equation 3rd. Okay, so that you can get uniform point spacing. Fine. Now I ask you to make a detailed note on this and let me know if there is any confusion. So just let me know like which PPT you want to see. Okay. So first make note on this. The entire derivation that we have done for calculating this along the scan line density and across the scan line density. If there is any doubt, then let me know. I will discuss that part. Okay. So in the remaining time, make a note on this. Then we'll do the this analysis, final analysis, how these parameters are related and what kind of trade-off we have. Is it clear?
Yes, sir.
So 1 by D is line density.
Which one you are talking about?
Sir, 1 by density across equal to line density, na?
Yeah, 1 divided by spacing between two successive points, laser footprints.
Okay.
Okay, so is there any doubt?